Hello everyone, and welcome to the In-Depth Engineering Capstone presentation. My name is Andrew Skavikis, and I will be presenting our project, TRAINN, Track Real-Time Artificial Intelligence Neural Network. Before we begin, let's meet the team. These are the technical directors for our project, Bill Matzizak, John Vernaglia, and David Helms. And our students, Giles Lanaway, computer engineer, myself, Andrew Skavikis, electrical engineer, Eric Gardner, also a computer engineer. An overview of In-Depth Engineering. It's a small business based in Middleton, Rhode Island. They mostly do work for the Department of Defense, making real-time, fault-tolerant, and highly available mission-critical software systems. In the past, two systems they have produced are the torpedo warning system and the submarine tactical control systems. Our project starts with data collection in two forms. One form, AIS, which is Automatic Identification System, and these are signals sent and received by maritime vehicles, and ADSB, Automatic Dependent Surveillance Broadcast, which are signals sent by aircraft. The next part of our project involves machine learning. So using the ship's path that we have taken from our data collection, we can figure out what type of ship or aircraft we are tracking based on its course. We do this by using a predictive neural network. And the final part of our project is plotting this ship's path. Many times before a ship does something illegal or it shouldn't do, it'll turn off its AIS receiver so we can't even see it begin to enter an illegal zone. But by plotting the ship's path, we can see these discontinuities and act on them. The anticipated best outcome for our project includes a data collection unit, which can store and decode AIS and ADSB signals, a neural network to classify the ships based on course information, and a GeoPlotter of vehicle track on Google Earth. Key accomplishments so far is a data parser to separate out useful information, a machine learning model for general ship classification, an AIS signal receiver for data collection, and a GeoPlotter built for plotting these received signals. The economic impact of our project is mostly for law enforcement. This can help with smuggling, illegal fishing, and catching people doing what they're not supposed to be doing. The next, I will be getting into my portion of the project, the AIS Signal Receiver. We're going to start with the equipment used for our receivers. So for AIS signals, what we've been working on this semester, we have an antenna specifically to receive AIS signals, a receiver for these AIS signals to decode them when they come through the antenna, and a GPS receiver for self-locating. The ADSB portion is not too much different. It needs a separate antenna and a separate receiver. And then data collection, we use micro SDs for holding OS and hard drives for holding large amounts of data. The signal receiver itself is comprised of three components. The antenna, which in our case is a VHF marine antenna operating at around 160 megahertz. This is a range for AIS signals, given that their signals are traveling between 150 and 165 megahertz. Our receiver, the QK-A026, handles both AIS and GPS signals, which is good for us because we require both an AIS antenna and a GPS antenna. And our microcontroller for handling data flow and task management is a Raspberry Pi. When we started out data collecting, we started with a program called OpenCPN. This software handles and can decode the bearing, latitude, longitude, current time, the speed, and the course and identification information of any ship that is transmitting AIS data within around 10 nautical miles, which was the range for our antenna. But we found a couple issues with this. It's hard to output the data files, so instead of doing this, we decided to manipulate the raw data. So from the AIS receiver to the Raspberry Pi. We can open up a serial connection to view the raw data coming in. And using a separate parser, in our case, we use a program called Data Logger. It can take this data and export it to a CSV file that's in a much nicer format than the raw data. In the upcoming semesters, we're going to be focusing on building an ADS-B receiver. During this semester, we have mostly focused on AIS receiver. ADS-B data collection is much different. The frequency is much higher. The signals need to travel farther distance. We hope to merge the portions of our AIS receiver for the machine learning and the GeoPlotter. We hope to build our device up for remote data collection. Our next speaker is Eric Gardner.
The most important aspect of our project this semester is our AIS data. As such, it is important to keep only the necessary data for our project to both reduce storage space and improve neural network performance. A parser was programmed in Python to ensure these benefits were hit. Below, we see an example of AIS data before it is parsed. It contains both missing data fields as well as irrelevant data for our project. After our data is parsed, these two aforementioned problems are fixed, and the result of that can be seen here. It does this by first keeping the columns we need and removing the columns we don't. It then removes ships with improper MMSI numbers or individual ship ID numbers, ships who are not moving or who are moored, ships with missing data, and ships without enough data to support classification. It then replaces the vessel type column with the vessel group column. Vessel types such as 1004, 1003, 70, and 71 are grouped together into vessel type 0, or cargo. Each of these individual groups are specified on the AIS website. Next, our data is normalized using min-max normalization. This ensures that all our data points are between the values of 0 and 1. This is important as it greatly improves the performance and speed of our neural network. Our data is then shrunk into smaller data types for smaller storage. This allows for more data to be input into the neural network. It finally stores our new parsed data into a new CSV file. This parsed data is now leveraged for our machine learning aspect of our project. For this project, a one-dimensional CNN was chosen as the model as it maintains the spatial relationship between time series data points. This is accomplished through the convolutional and pooling layers that are typically absent from normal neural networks. Our parsed CSV file is then input into a script for our neural network. This script splits the data into two, a trained dataset and a test dataset. It then iterates through each of the ships in each dataset and resamples and interpolates them so they each have one sample taken every 10 minutes for a contiguous 12-hour period. It is important that each time series has the same amount of steps, as this is the only legal input for a one-dimensional CNN. This results in two 3D arrays which are ready to be input into the CNN model. Our model is programmed using TensorFlow, an open source library for machine learning used by companies like Google and Intel. The CNN model then gives a prediction for classification type. Below is an example of an incorrect prediction our model made. The first array shows that the ship is of type 6, but our model believes it should be of type 0, as type 0 has the highest number out of all the other arrays. For next semester, I will need to tune hyperparameters for our CNN to improve performance. This includes changing the learning rate, amount of epochs, and possibly different activation functions. As of now, our model is able to predict a ship type within a range of about 50 to 70% accuracy. I will then work on the parser and CNN model for our ADS-B data. This should take much less time than it took this semester, because it should be fairly comparable to the AIS parser and model. Giles will now talk about the final aspect of our project, the Google Earth signal plotting.
Thank you, Eric. Hello everyone, my name is Giles Lanaway. Today I'll be speaking about decoding AIS messages and the GeoPlotter function of our project. As Andrew has already shown you, our Raspberry Pi setup allows us to record data as a stream of messages from the AIS Signal Receiver. The data logger program outputs the CSV file seen on the slide. This data is a mix of GPS and AIS signals. The AIS data can be picked out easily by looking for the exclamation point at the beginning of the data column. For the CNN model, decoding GPS signals will prove useful to normalize our data's timestamps. This is because GPS time data is much more accurate than AIS. However, for the purposes of the GeoPlotter, only decoding AIS data is necessary. A simple parser in Python separates the AIS data from the GPS data and stores it into a file to be decoded. To decode this newly isolated data, an open source program, AIS Util, was used. The program's output is shown on the slide. Columns of use to our CNN are the ship's MMSI, date and time, coordinates, speed over ground, course over ground, its name, and the vessel type. All other data can be stripped away. What is left over is input to the CNN. For the GeoPlotter, only the ship's identifiers, timestamp, and coordinates are needed. Using the open source Python library, PyKML, a custom program creates a new KML file for every ship. The track scene is the result of importing the Block Island Ferry's AIS data into Google Earth Pro. The format of each file is simply a pin and a line string. The pin is the first coordinate recorded, and the string is a combination of all other coordinates received by that ship. Looking forward to next semester, my main priority will be to start recording ADS-B signals as soon as possible. A decoded sample image is shown on the right. After the signals have been recorded and decoded, I will be able to apply a similar plotter function. This will hopefully allow me more time to assist Eric in training the new CNN and Andrew with the continued assembly of the final product. Here are some of the more important Python libraries we used for this project, as well as any open source programs. Now that being said, our group would like to thank each of our technical directors for the help and mentorship they have offered us. We would also like to thank our URI advisors. That concludes our presentation. We hope everyone has a wonderful break and we'll be looking forward to working together again in the spring. Thank you.